review the SDRAM material? How is it so far? Are you facing any challenges or didn't have chance yet? Okay, never mind lah. If maybe it's a long day for you, I just start the lecture lah. Okay. Right. So today actually will be the last part of the material I want to share with you lah. The FPGA. Next week we can still meet, but I think it'll just be more of Q&A lah, because I pretty much can cover everything by these 2 weeks lah. And the remaining time we have, maybe it's more like we can make it more like a tutorial lah. If you have any questions about the design, you want some specific help and all that lah. Okay, today we're talking about FPGAs, and it's another acronym for field programmable gate arrays. Okay, and I've updated the slides already for this. Here you go, you can see this. So it's the new slides are here, and then I've got also 2 articles to share with you on FPGA. You can go and read for further details. They're very recent ones. And later I'll add today's video here for your reference. But today we'll just be going over, try to get a more deep understanding of FPGAs and why it's interesting to know about them, and how could it be a little bit different from ASIC, application specific integrated circuit, and we'll just go deep into it. Okay, so the first step is to understand the key idea here, okay, for FPGAs is they're just a kind of a special circuit, right? It's a programmable circuit. It's a little bit like microprocessor, but not quite, because microprocessor you have fixed set of instructions, okay? In FPGA you have fixed set of logic function approximators, right? So what if you think about it, right? If you think the combination logic, you can actually write it out in terms of Boolean logic, right? Output Y is some Boolean combination of some inputs, right? So that's a logic function, right? Because you have inputs and then there's a function and you get output. So FPGA is sort of a digital logic approximator. And the key idea of FPGA is, number one, they are approximating digital logic with lookup table. So if I can implement and program different kind of digital logic with lookup tables. Okay, so I'm using my combination logic is pretty much a lookup table, and it is the same idea as using lookup tables for ROM and multiplexers, and we'll cover that later, just after this. But the key idea here is, rather than using discrete gates like AND, OR, and NOT, I'm using a lookup table to actually program my logic with memory. Okay, and because of that, I define my combinational logic by a lookup table, so I can actually program my combinational logic, and then whether it's got a flip-flop or not. Because remember, when we discussed last week, all your state machines are basically combinational logic, go into a flip-flop, go into a combinational logic, go into a flip-flop. So if I'm able to implement my combinational logic as a lookup table, then I throw a flip-flop around that, in front of that, then I can have another lookup table. Then pretty much I can program any state machine, right? Yeah, I can. And the second thing here is I'm actually able to program the wiring or the connection or the routing between these combinational logic lookup tables. So let's take a step back and let me talk about what is it like to implement a logic as a multiplexer and a lookup table. Okay, so here let's think about this logic here. Okay, let's say I want to give you idea of a NOT gate, 0 and 1. The output is going to be 1 and 0, right? Do you agree with me? Do you agree with me?
Yes.
Okay. I've not covered this with you, have I? Multiplexers, how to implement logic.
Haven't. Last week we
haven't.
Just go SDRAM. Yeah.
Okay, so if I want to implement this as a multiplexer, I can set A to 0, I can set B to 1, logic 1, and C is actually my input, and O is my output. You can follow me? Does this make sense to you?
Yeah, understand.
Yeah. Okay, great. Now, if I actually want to do an AND gate, I want to simulate an AND gate. Okay. How would I do it? I would actually have A equals 1. A equals whatever A is lah. Okay. is a one A equals input bit 0, for instance, B equals 0, C equals input bit 1. Okay. Do you follow that I can use this as a way to actually specify a AND gate? So if I set C to be input 1, so if input 0, then B will be 0, of course. And if input is 1, the output will depend on the value of A, which is input 0. Do you follow this?
Yep, understand.
Understood, huh? Okay, in the same way I can do for OR gate. And here is the same thing, except that maybe this is input 0. And this is definitely 1, something like this, okay? So I've just showed you how I can actually create the 3 basic logic gates and or not using a multiplexer. Therefore, we have said before, I think this is something you've covered in digital electronics. If you can implement AND, OR, and NOT, you have these 3 functions, you can implement any digital logic, any combinational logic. So which means that multiplexers can implement any combinational logic. And you notice the way I put this multiplexer is, I'm just assigning certain input and output. So C is actually something like a choice, and either I put a fixed value in A and B, or I let that be an input and then I get an output O, correct? And the way we are specifying this is we always have a truth table, right? Which is basically inputs and the output, right? So the truth table is always telling us, given this input, what is the output? Given this input, what is the output? Correct? You agree with me?
Yes.
Right, because a truth table is actually specifying your function, right? Because you got only a discrete number of combinations. So if I got 5 inputs, I can also have outputs like 5 or 10, I can specify any logic this way, right? The way I need to make my logic complete is I make sure that for all the combinations of inputs, the output is specified. You agree with me?
Yeah, Doctor.
So that's the idea of a lookup table. The idea of a lookup table is that I can put, let's say my inputs is 2 bits. Okay, this is all the possible input combination. I can specify my outputs. Okay, my output can be 1 bit, can be 2 bit, can be 4 bit, can be 8 bit, and so on. Okay, right. So whatever I put in as an input, as long as the whatever I put in as an input, I can get the output. That will be implementing my logic, right? You agree with me? So whatever input I put here, as long as I get the output here, it doesn't really matter how I implement this, right? I can implement this with logic gates and or not, or NAND and NOR. I can implement this in multiplexer, but what I care about is for a given input pattern, I must be able to get the output, whether the output is 1 bit or 2 bits or 5 bits or 10 bit. You agree with me?
Yes.
So you got the idea of a lookup table. Okay, now this is where it gets interesting. Have you seen a lookup table before? Yes, in practice you have actually seen a form of a lookup table. If I call this your address, and I call this your data, what does this look like to you? So here I have 2 bit 2-bit address. And here let's say I've got 4, 8, 12, 16. What does this look like to you?
Register, Doctor.
Register, it looks like a form of ROM or memory, right? Not quite register. Register is actually another word for single flip-flop, but you are on the right track. This actually looks to you something like I think your word is ROM because you can't write it, right? It's already saved, or it's a kind of memory, all right? It's a kind of memory, right? You put in the address, the data. So you can actually implement a lookup table with a ROM device or a memory, correct? You use the inputs as the address and the output itself is the data. Agree with me?
Yes, sir.
Okay, right. So, and this is kind of nice because whereas in digital logic, depending on different sets of inputs, the propagation delay will be slightly different and sometimes very, very different, right? In a lookup table, the read and write delay, do you think is the same or is different or how? Okay, what do you think?
For my yes, they have a different delay, doctor, because they have their own data path.
Why do you say they have different delay?
Since for example, for ROM, we are writing something in it, right?
Can you write something in ROM?
Sorry?
Can you write something in ROM? Can you write something in ROM? I don't know, Hima, I'm not understanding your statement.
For ROM, you can only use. You cannot write on ROM. Hello. For just now, the question.
Ready không?
Okay.
But for ROM, actually we just assign the values, right, inside the address, right? We are not writing it.
Yes, should be.
Hi, sorry, connection a bit bad. Can you say that again? So what would you expect for, let's say I implement it with a ROM, okay? Would you expect for different value of input, would you expect the propagation delay at the data, the output to be the same or to be different?
You mean the propagation delay might be the same?
Okay. Yeah, that's actually kind of the ideal lah, because roughly the access time in memory is roughly about the same lah, unless you're going into dynamic RAM. But for static RAM, usually the propagation time is the same lah, because whatever address you put in is kind of a random access, right? So propagation time will be the same lah. That's kind of the answer that I'm looking for lah. So you can already see from here that a lookup table has a bit of advantages. It kind of makes the logic propagation time about the same lah. Okay, do you follow that?
Yes, understand.
Okay, do you follow that I can now use a lookup table, which is, it's sort of a memory element, right? Because I put in the address, I get the data. It's a memory element, right? You follow how lookup tables are like that, right?
Right, understand.
And I can implement the logic, and all that I'm doing is I'm just specifying the inputs and the output. The output is what I save into that lookup table lah. I don't need to write into it. I mean, I need to write it lah, but I write it once, and then I can use this whole memory element as if it's a combinational logic. You understand? That's the key point here. If you take home this point, you already understand a lot about FPGAs already, right? Because the key idea here is, rather than using discrete gate, an FPGA is using lookup tables to implement digital logic. Okay, so the way you will program your digital logic is you just specify what is the output at that particular address. So instead of a ROM, you only program it once and you can't change it. But FPGA is sort of like is a RAM, right? The lookup tables are actually RAM. You store those bits in the RAM, Okay, and then you are just doing, when you're doing digital logic, you're doing computation, you're just putting in inverted commas the address of that RAM, which is the input to that RAM, and then the output is being read out. That's the value of your digital logic. That's why I like you to think about this as a function, right? A function, you put in an input, you get an output. So here your combinational logic is actually a function. For a given input, you get an output. And the best way you can specify your function is through the truth table. Okay, that key idea, right? Okay, so I'm just going to move on because I guess a bit difficult to get your answers sometimes. So I just, if you don't understand, you just stop me. Okay. All right. So why do we care about FPGAs? What is the issue about FPGA? What does it make it so attractive lah? So it started a long time ago, I think in the 1990s lah. And if you look at this curve, you look at the dotted curve first. Okay, the dotted curve is what we call an older process technology, and the solid curve is actually new process technology. Okay, so older process technology means it's larger nodes lah, like 100 and like 1 micron, 500 nanometers and all that. And then the newer process technology, the transistors are smaller, so the value is actually smaller lah. Okay, so in the older days, the ASIC has some kind of fixed cost here, right? Because you have to actually hire the engineers, you have to build the tools, you have to pay the cost of the fab to turn it up and all that. So there's a very high starting cost. But as you increase the number of units that you purchase, the cost only goes up very, very slowly lah, because it's just the cost of the wafer after you paid the cost of making the chip and all that lah. Okay, so if you produce many chips, the cost per chip goes down because you amortize the cost of the chip lah. This is the idea behind ASIC, application specific integrated circuit. These are the ICs that you see. Whereas for the FPGA, the idea is something like this, like the company Xilinx or now Intel, they make the FPGAs, they bond all the costs, so they just sell you a product. But you as the company or the designer, your cost in terms of number of units is proportional to the cost is actually proportional to the number of units. You don't have a non-recurring engineering cost. You don't have like an overhead, right? Because if you want to actually buy sell one FPGA, you can actually make like a 10 you can actually make a design only for 10 chips, something like that, right? And it will just cost you 10 FPGA units. So that's the attraction of FPGA in the initial point, that the cost to actually get a programmable, a specific circuit, hardware circuit that is customized, and that you can actually use, the cost of that for FPGA is much cheaper than the cost of ASIC. Okay, whereas the cost for ASIC, you need to get volume first, then it makes sense to actually work on it. So it provides a low entry point. And what we are seeing is that over time, as we are trying to implement the FPGAs with better and better fabrication technology, that means the transistors are smaller. The cost for ASIC actually is going up, the non-recurring engineering cost, the overhead to even get started. Why? Because as you make smaller and smaller ASICs, the fab and the kind of engineering work you need to in order to achieve that is actually more. Because the devices are less reliable and it's harder to get them to work, right? But for FPGA, it's the opposite problem. As you increase as you go to better and better process technology, the cost for the FPGA is actually going down, right? Because the device is smaller, you can pack more logic and units and all that. So over time, FPGA becomes a more and more attractive, cost-effective, and attractive option to implement logic circuit, dedicated logic circuit. And again, here I want to compare and contrast lah. If you talk about programmability, most of you will just think embedded controllers. I just buy a microprocessor and all that. That's one way you can do it. But the interest in FPGA is because FPGA is a special purpose logic. They tend to be faster because you don't have the fetch, decode, ALU, and store cycle, right? That if you want to implement a logic, it's just that already. It's just one clock cycle, you get the logic. Whereas for microprocessor, if you want to do an AND, you actually have to have an instruction fetch, decode, ALU, and maybe you store the device, the value back into your register or into your memory. You need to have all the stages of that pipeline. So for sure, FPGA, if you can custom program that, or for an ASIC, it's going to be faster than a microprocessor, because for microprocessor or microcontroller, there are fixed number of computation cycles because it's a general purpose. So this is the reason why we're going for FPGAs, and over time FPGA become a more and more attractive option. Okay, and it's more and more attractive because you will soon see that over time, as you're going from, let's say, old process technology, 500 nanometers in 1996, the delay for about the logic interconnect is roughly in the order of 4 to 6 nanoseconds, right? And you can only maybe squeeze about 200 types of programmable lookup tables on it, whereas around 2002, that's about 10 years ago, 130 nanometer, you can actually squeeze almost 5 times as much logic capacity, and the delay is 5 times less, right? So FPGAs are getting better and better. And if you start look at it now, the FPGAs from 10 years ago is equivalent to the ASIC density from 20 years ago, right? So FPGA has grown to become able to actually program entire chips, not so big chips, but decent sized chips, chips that are almost, I would say, almost 1 million gates or more, right? So this is 1,500 logic gates. This is 1,500. 1.5 million logic gates is this roughly around this line. So right now our capacity is designs that have roughly about 2 million to 2 million logic gates. You can actually implement them completely with FPGA. And what's actually very interesting is the cost of a $10 FPGA can now implement something roughly like a design with maybe about half a million or close to 1 million logic gates. So FPGA used to be, in the early days when they were created, they used to be the devices that when you want to actually interface between chips and all that, you just put an FPGA, because if you want to put discrete circuits, you have a lot of ICs, so maybe you just put an FPGA. Then as the gate density, the number of logic that can be implemented in FPGA increase, they started taking on a bigger and bigger share of the market. And at some point, FPGAs become the technology of choice for small ASIC design. So nowadays, when you actually have a small chip that you want to make, you're most likely better off just implementing it in FPGA. It's going to be faster, cheaper, less risky and all that than if you go for ASIC. So ASIC only sort of makes sense now for very large designs, like the most complex microprocessors, GPUs and all that. If you are talking about some kind of dedicated circuit that is not too big, few 100,000 logic gates, you're far better off. You can implement the entire design in an FPGA. And so we are now going to see that there's an evolution of FPGA. In the early days, is just about programmable logic, right? Can I just implement a combination of logic? Then as time goes by, they try to cram more and more logic, and then give you more power to create more and more sequential state machines. Okay, and after a while, when the number of logic gates and capacity of the FPGA grows so big, at some point there's a shift in the FPGA where instead of adding more programmable logic, they start putting in customized fit-for-purpose circuits. So it's FPGA today is not really like the FPGA from 10, 15 years ago. It's not just programmable logic. You actually have, let's say, a high-speed serial transceiver. So some of them can do PCIe and all that. This is not programmable logic at any chance. It's a very dedicated circuit block. It probably has some programmable DSP. It's got actually dedicated RAM. They're not using the flip-flops anymore already. There's actually a dedicated RAM inside the FPGA, and then clock management, you can change the clock and all that. And then some of them also have dedicated processors. It's no longer I synthesize the processor, I implement the processor in terms of FPGA. Nowadays, they include dedicated processors in the FPGA. Okay, so the design flow is roughly the same like ASIC, but there's still a few key differences. So the first is you actually specify your logic by typing up a Verilog RTL. Okay, Verilog RTL, as we discussed last week, is nothing else but you are describing the combinational logic, and sometimes you're describing the combinational logic going into a flip-flop. Okay, it's just telling how you are transferring logic, the function, the logic function that's going to go into a flip-flop. So the basic task that the automation tools will do is 3 steps usually. It's called synthesis, placement, and routing. Okay, synthesis, placement, and routing. So these 3 steps are the same for FPGA and for ASIC, but they have slight differences within them. So the synthesis step is just converting your high-level description into low-level logic gates. Okay, and if you have ASIC, normally there is a fab that actually tells you I can make this set of AND gates, I can make this set of OR gates, and then I've got the timing and all that. So the synthesis process will convert your RTL logic in terms of the basic AND, OR, and NOR gates, or the basic NAND and NOR gates, or there's some other complicated gates. They'll convert it in terms of the logic that is available that can be made by the fab. Okay, for FPGA, it converts it into the basic FPGA elements, and these are basically the lookup tables. Okay, and we'll talk about that later. But here, synthesis, I want you to understand, it's just a process of translating your high-level register transfer logic from Verilog into a low-level digital function, which is either implemented as basic gates that the fab can make, or basic logic elements that is in the FPGA. So the second step the tool does is once it says, okay, this logic that you've actually created in Verilog RTL can be implemented with these basic logic gates from the fab or these basic logic gates from the FPGA. I'm going to decide for FPGA, I'm going to decide where in the chip are these resources, because your FPGA doesn't have unlimited logic primitives, right? It doesn't have unlimited logic units. It's got a fixed number of units, and they are certain position around the FPGA chip. So the placement step is just identifying, I'm going to use this one at the top left corner, this one in the middle for this. So it's identifying which to put it. In an IC for ASIC, the placement process is actually, you've got a particular area, you can actually put in that logic gate, you place it here, you place it here, you place it here, because you have to arrange the logic gate somehow onto the chip, right? So the placement step for ASIC is doing that. And then the routing is the final step, where it's actually creating the wires to connect all these logic up so that they obey your design. Okay. And again, there are some constraints here for ASIC, for ICs, the application specific ICs, ASIC. The routing is done for maybe up to 7 layers or a few set of layers, and you cannot have unlimited wires and then if you actually and I think you can start to see that the placement and the routing itself have some good relationship, some very close relationship. If you actually place gates that are connected to each other very far apart, you will soon run out of space and wires to crisscross. So gates that tend to be very close together, that have to be connected together, you try to put them together so that you can cut short the length of the wires, and there are certain constraints on that. And even in the FPGA, the routing problem is also a problem of connecting up certain logic blocks to another logic block to implement your logic function. But here, there are a fixed number of connections, wires, and there are only fixed number of ways you can connect them up. Okay, so I want you to understand that the synthesis, placement, and routing step, this is all done automatically. There are tools that will do this for you. In ASIC, it's very expensive, these tools. They call them the EDA tools, electronic design automation. It's basically computational algorithms that optimize all these. So from you as a designer, what you do is you just click the button and then you let this go, and then you see whether it's able to do it or not. So you have to understand that. And in terms of the FPGA design, when you're actually designing to implement an FPGA, you just need to write the Verilog in such a way that it will be able to synthesize, and then you can place and route it. Okay, so once you can write your Verilog RTL, you just click a button, it will do the synthesis, placement, and routing for you. Okay, but there's one key point here, okay, and it's a practical point. That is that in the FPGA, is trying to identify where to place each of these logic elements, and you also are not using the FPGA as a standalone chip, right? Normally, FPGAs will come on a development board. And that development board will have certain I/O pins that you can connect to certain headers or connectors, or they'll be connected to certain ICs like memory, like your Ethernet controller, like USB controller. So that the pins on the FPGA are already occupied, because in order for you to make the development board to run the FPGA, you have to assign certain pins to certain devices, right? So this is where you already have locked certain pins. If you want to access that device, or you want to use that other device onto the board, you need to actually connect to those pins lah. So because of that constraint, when you're programming the FPGA, you have to watch out lah for those pins that you need to use, that they're already connected on the board to something. You have to force the FPGA to reserve those pins for certain outputs of your design. Okay, and that's called the pin assignment file. So the only thing you need to do besides writing the Verilog RTLs, you need to identify how to assign the pins on your physical FPGA chip, so that the algorithm will know where to place the logic, how to route it and all that, all right? Is that part okay? Do you follow so far? We've not gone into any details, just a very high level at this moment. Do you understand the steps?
I understand.
Sorry, is that a yes?
Yes, I understand.
Okay, right. Okay, now we are jumping into this basic concept of what is a programmable logic element in an FPGA. Okay, so I think you all are familiar with the K-maps, where all your logic function can actually be a Boolean lah, like you have a AND, OR, and a NOT lah. So if you have a set of NOT gates, AND gates, and OR gates, you can implement any logic function. So in the old day, there was a type of programmable logic called PAL lah, programmable array logic, where the inputs are just going into a set of gates, NOT gates, AND gates, and OR gates, right? And what they do is they actually they have a switch matrix here where they actually turn on the connection, whether this connection will connect to this gate or this connection goes to this gate and all that. So the way you design your programmable logic in those days with PAL, this is about 20 years ago, is you just specify these locations lah, but you still are implementing your logic with discrete gates. It's just you are programming or configuring the connectivity of the wires. FPGAs do not work like this. This is old. FPGAs do not work like this. Rather, FPGAs work like this. If you look at this, this is a bunch of, I'll say it's SRAM lah. This is a bunch of SRAM bits lah. Okay, each of these is an SRAM bit, and the SRAM bit is basically controlling. Are you sending this A bit into how are you sending this A bit towards this out bit lah, right? So you have a bunch of input bits, you have one output bit here. Okay, so this actually is a bunch of digital multiplexers. This is a bunch of multiplexers. It's actually a two-stage of multiplexer where you can either specify a high or a low going out of this value, or you can actually specify an input going out at this. So this is how the lookup table is implemented in modern FPGAs today. The program will be here. You will actually at some point store your bits 10100101, and these bits will choose, how do I send A out into this? What is the conditions in which I send A or B or C or D, or how do I combine them? So it's implementing actually a two-stage multiplexer here, and the logic of how things are connected is dependent on the SRAMs, whether they enable or they disable a particular connection. Okay, so this structure, okay, is what they call the K lookup table. K actually stands for the number of inputs, because remember, when we talked about it earlier, the lookup table, the number of entries in the lookup table depends on the number of input combinations. If I have 2 bits, I need to have specified 4 possible outputs, because there are only 4 possible combinations. If I've got 4 bits, I have to specify 16 possible outputs. So my lookup table actually depends on how many input bits I have here. So a K lookup table has K inputs, and therefore there are 2 to the power of K possible values that this K lookup table must be able to specify on this output. So this is a K input, 1 bit output. Okay, this function, this lookup table is implementing for taking k inputs, 1-bit function. So k normally is 5 or 6 in a FPGA, one basic unit. And basically it's connected to a flip-flop here. And it can either bypass the flip-flop, or the output of the flip-flop can be fed back together, or the output of flip-flop can be selected between these two, right? That's either going to the output or routing. Okay, so this is the basic digital, the basic logic element in an FPGA today. It comprises of a lookup table with k bits, with the option whether you want to throw in a flip-flop here or not. Okay, what do I say as an option? Because you have a bunch of other SRAM bits here that would say either this bit will come out through here, so that the SRAM bit will just set this multiplexer so that the bit is going to the output here. So you bypass the flip-flop, or if you actually want to use the flip-flop, you will set this multiplexer bit as this multiplexer to send this bit to the output, right? So you have the choice to choose whether you want this flip-flop at the output of this k input lookup table. And this is called the basic logic element. And the way this is arranged in an FPGA is you've got a bunch of basic logic elements here. Each of these basic logic elements is a k input lookup table. So each of these lookup table, you can specify the logic by SRAM. And then there's something called a crossbar. A crossbar is basically you got a whole bunch of inputs, it's going into multiplexers, and you can actually control which of these inputs is going into as acting as the input to this basic logic element. And again, this multiplexer, the control bits are coming from an SRAM. So you are programming functions of the inputs going into the basic logic element. You are programming the logic function that's implemented in the basic logic element, and you are also programming, okay, which of these outputs is actually being sent to which output lines. And these configurable logic blocks, there are a bunch of them that are put throughout the FPGA. So that is the basic structure of an FPGA. Okay, at this point, I need to check with you. Do you understand how digital logic is implemented in the FPGA? Do you understand that the programmability is actually I can program the logic function, the lookup table, and I can program the wires, the connectivity? Do you understand that?
Yes, okay.
Okay, great. If you understand, good, we move on. So the basic elements of FPGA is you program the logic, the lookup table. There are a whole bunch of them. They are the basic logic elements, and then there are a whole bunch of them grouped together, and then they form a logic block. And then there are also, later on, you will see that there are a whole bunch of logic blocks, and then there's a hierarchy of connections called switches, where you can connect all the interconnection. So if you have enough inputs here, then that small portion of the combination logic can be implemented here. If you don't have enough here, you have to start combining 2 or more logic blocks to implement your complicated logic function. Okay. The third is, second is you have to program the routing, that is which wires are connected, which inputs, and then this will compute certain things, and then the outputs here will also be connected as inputs to another stage. So how do I program that? And third, there's the other option, which is the programmability of the I/O of the chip. We'll come to that shortly. Okay, so with these 3 basic programmable elements, the program for all these connections is stored in static RAM. Okay, so the static RAM is actually setting, turn this on, turn this off, and all that. So this thing is not changing. This static RAM is not changing while the circuit is operating. This is configuring, just saying that which path the logic table will take. These wires, this routing, these are not changing when the circuit is operating. It's already fixed in that static RAM. What is changing is only these input pins, and you get outputs based on whatever the inputs are. Okay. So how are FPGAs programmed? So the way you program an FPGA is you make sure that all these SRAM bits that are setting the connectivity of the logic, the lookup table, the connectivity of the wires, that they are set. So you have to set all these SRAM bits. But there are so many of them in the FPGA, right? So how do you put them in? We use something called the IEEE JTAG interface. The JTAG interface is actually a a standard that was created for testing sequential logic. And the idea is something like this. Within your chip, you could have like millions and millions of flip-flops, okay? And it's not possible for you to look up and check the value of every single flip-flop because you don't have that many pins on your chip. So what JTAG do is to allow you to test is it has an alternative connection where all the flip-flops in your chip, right, are connected as a shift register. So if you're not operating in JTAG mode, then your flip-flops are functioning like whether it's a processor or whether it's an FPGA, it's functioning like that. Then you have the option that you can actually switch it to become JTAG mode, and all of a sudden all the flip-flops are chained together as a shift register. You have a controller that puts in a clock, and then it will shift out all the bits on the flip-flop serially out through one pin. So this way you can actually test and read out all the flip-flop values frozen in time. You just read them all out serially using the JTAG interface. Okay, so FPGAs take advantage of this interface. Okay, so you are actually doing on your CPU your computer, you are synthesizing it, you're doing the placement, you're doing the routing. After you do the synthesis, placement, and routing, the FPGA software will come up with a long string of binary values, which is nothing else but the setting of the SRAM at that position, either to connect or disconnect that lookup table, that route, that wire, and all that. And then that FPGA, that CPU is going to connect to a JTAG controller, and that JTAG controller is going to send a long serial string of bits into the FPGA, and the FPGA is going to actually push that serial string of bits into the SRAM. But it's got additional control logic. You will read it serially, then you'll buffer it, then when there's a parallel data word, it's going to update and write the SRAM in its own internal way. So do you understand how FPGAs are programmed?
So basically, we just choose the SRAM data from the controller of the JTAG, right?
No, you don't even need to choose any of that. Remember, your steps is just you write the Verilog RTL, and then you click the button that does the synthesis, placement, and routing. And then you might need to specify the pin assignment first. What happens once you click the button on the software? It does the synthesis. It will identify, okay, this particular logic, I'm going to use this lookup table. Okay, this particular logic, I'm going to use this lookup table on this part of the chip here. This particular logic, I'm going to use this lookup table. This particular logic, I'm going to use this lookup table. So that is synthesis. Placement is this lookup table, this lookup table, this lookup table. Routing is I need to connect it up here. So once your FPGA does this automatically, it will know how to set each of these individual SRAM bits. And then the software will generate automatically a program file, which is nothing else but the setting for all the SRAM bits in the FPGA. You don't need to do anything. You just click the button only. Okay. And then you will have to connect it to a JTAG controller, and the JTAG controller will use the JTAG scan chain to update the SRAM of these wires and the logic block in the whole FPGA. But you, as the designer, you don't really see all of that. All you do is you click the sys, placement, routing, you specify your pin assignment. You specify your pin assignment first. You click synthesis, placement, routing. That one, the chip does everything. The software does everything for you. And then there's a button that says program. Right. Program is just this part here where that setting of the SRAM's bits will be pushed into the FPGA.
Oh, okay, understand.
All automated for you, but I'm trying to let you know what happens behind this. Why are you programming FPGA? Why do you need to click all of this? This is what's going on in the background. So the synthesis, placement, and routing, this is the same like ASIC, but FPGA tools do a step further. Once they can map and position the entire design into your FPGA, and then they have the configuration of all the SRAM bits. They are going to extract the configuration of all the SRAM bits, put it into a long serial bit file. That's why you have a bit file, which is just a sequence of ones and zeros that is going to update the state of all these connections. And then you will use the JTAG interface to program it. But you actually don't have to do much. It's just you click program and it goes, you just program it like that. Okay?
Okay, understand.
So I just let you know this programming is actually under control of what they call the JTAG tag controller lah. You may have actually encountered this in Dr. Bamazu's class where there's a state machine for this controller, and this is kind of the idea lah, their instruction bypass. So there's sort of like a small little processor which is the test access port controller lah. This is the mechanism by which the FPGA uses this to program. So on an FPGA chip, you have this JTAG controller, either on the FPGA chip or in the FPGA board lah, but I think nowadays it's on the chip, and this is the FPGA lah. This is all internal to the FPGA, you don't see this, right? But if you want to know what happens, they are using the JTAG resource to do programming. JTAG was defined for testing of digital circuits or logic in digital circuits, but they're using this to program the FPGA, okay? Okay, if you understand that, now let's go a little bit more into detail to think about, try to understand if I'm an FPGA designer, why do I care? How do I care about this? Why are these things also important, right? Let's try to understand that a little bit more. So FPGA, you kind of have some design constraints lah. The key idea is you need to know how much of logic capacity you have lah, right? Because you're trying to implement some kind of complex design, right? At the simplest level, you have a certain number of inputs and you need to get a certain number of outputs and you need to implement that, right? So you need to make sure that the FPGA that you choose has enough logic capacity, lah, okay? And FPGA designers always struggle lah, because as you can see, this is actually, the programmability is taking up some space lah, because you need the SRAM, you need to be able to set certain bits to connect, not to connect, and all that. No? So it takes a bit more area than a conventional logic gate for an ASIC. Okay, so that's one disadvantage of FPGAs. And in the earlier days, the delay was actually higher and it actually consumed more energy, right? Because you've got all this additional programmable infrastructure to allow you to program this. But it's okay lah, it's an acceptable cost because of this curve. For a certain number of units less than some point, it is actually far cheaper to actually implement your design in FPGA and to sell the FPGA directly. And as we improve in process technology, that number of logic is actually higher. So to this point, I would actually say that if you're looking at maybe like something like 1 million logic gates or 500,000 kind of logic gates, don't even need to think about ASIC anymore. You're much better off implementing it with an FPGA, right? So, okay, I think I don't talk about the flip-flop. I think I confuse you all. But one of the things that the designers have to do is they have to choose what is the size of the lookup table, right? Because the lookup table again is the smallest block where you can implement a combinational logic, correct? And if you actually have this to be too big, let's say you have a 10 input lookup table, then it so happens that for your particular state machine, you have only like 2 or 3 inputs for most of the paths before the flip-flop, then you'll be losing a lot of these combinational logic because you cannot use them, right? Because they are already like kind of wasted lah. Whereas if you have them too small, you need to combine multiple lookup tables and that incurs additional penalty because again, to combine additional lookup tables, you need to go through all this routing logic and the wires are longer and all that. So there's kind of like a magic number. So what I here want to kind of highlight to you is the FPGA designers have found between 5 to 6 input per logic block is okay. And here they do something a little bit smart. They actually implement a 6 input lookup table, but such a way that you can implement 2 individual 5 input lookup tables inside this 6 input lookup table. This allows you to save additional logic, especially for small designs. So this is among some of the innovations that FPGA designers do to try to reduce the costs and make the FPGAs more attractive. Okay, so now we've just talked very quickly already about the basic programmable logic element. What does it look like, right? It's basically a bunch of SRAMs that is controlling some multiplexers, which can be connected either to VDD ground or to inputs. And outside of this K input lookup table, there's the option to actually tag on a flip-flop or not. And then you have a bunch of them connected to get together with some kind of feedback connection where you can configure this wiring via multiplexers again, and these together, and then you can also configure the output via multiplexers, and this is a logic block. Okay, so we have covered the programmability of logic blocks. Now, at the higher level, you have a programmability of the logic block, but this is not such a big logic, and what you actually need to do with a bigger design is you need to combine multiple logic blocks together, and you need to combine the inputs of the logic block or the output of the logic block. You need to take it to the pins of your chip. So FPGA actually has a routing matrix, which is basically a bunch of wires here and there. Is what is called a switch. So this is like the example of a switch. You have all these wires going in. Let's say there are 10 wires here, and all these wires going out. Let's say there are 10 wires here. So a switch is able to say, for this particular wire, are you going to send this output here, or are you going to send the second output here, or the third output here, or the fourth output here, or the fifth output here? So you are able to choose which wire gets sent to this. But there is a limitation. It's not like you can send all the wires onto the same line. If one wire is already taking this line, the remaining wires have the other 9 choices left. So this is a switch. So there are two types of arrangements in FPGA where the connectivity between logic blocks is achieved. One is what we call the hierarchical routing, which is what you see here. The logic blocks are connected locally through a small switch, and then groups of logic blocks are connected at a higher level through another switch. And then this group of logic blocks can be connected to this group of logic blocks through these switches, these two switches. And this set of logic blocks can be connected to this set of logic blocks using this switch. The other style of routing is called the island style routing, where you have logic blocks here and they are just kind of tiled all together, and you are actually depending on these local switches to connect this one to this one to this one to this. So if you're interested, this architecture is actually used by Altera and now Intel. So your FPGA that you are using is actually following a hierarchical architecture, and Xilinx, the market leader, is actually using this island architecture. But I would like to alert you that this switch is nothing else but a bunch of like multiplexers that look like this. Either you can think about that as a pass transistor. You turn this on, the logic goes through. You turn this off, this is floating. Tri-state buffer, which is the same thing. You turn this on, this is true. You turn this off, this is not going through. Or you can think about it as a multiplexer, which is buffered. You choose which of this output goes out here. They're kind of equivalent and they'll be implemented in different ways, but it's just to let you know and that you understand that the switch is not something magical. It's comprised of all of these. So you're just choosing which wire connect to which wire using one of these configurable switches. All right. Okay. So this is the FPGA routing, and again, you don't need to do any of this. The tool does this all automatic for you. I just repeat, you are just writing Verilog RTL, and you're just saying at the end of the chip, this pin goes to what logic, and then the tool will figure out, okay, I'm going to use this logic block, I'm going to connect it by this line here going through it like that, and then I'm going to connect to the output by going like this line here, going this path here and all that. The tool does that automatically for you. But this is how an FPGA works. So this is the programmable routing. So the three basic elements: programmable logic. How am I choosing my lookup tables and specify my lookup tables? Programmable routing, which is how am I connecting up all the logic blocks in my FPGA to the outputs and to one another. And the third, programmable I/O, the third element. Now, I think you know that digital logic has multiple logic families, right? You have 5 volt TTL, 3.3 volt CMOS, 2.5 volt CMOS, 1.8 volt CMOS, 1.1 volt CMOS, and something called LVDS, which is on the order of 100 to 200 millivolts, low voltage differential signaling. You know that, right? That the different type of digital logic standards, right? Hello? Yes? No?
For me, no. So
okay, so I'm just letting you know like
okay.
logic 1 does not just mean it's 5 volt or 3.3 volt. That's very old already.
Oh yeah,
You
this
have
one is
a bunch of standards where it actually can be defined by the supply voltage the VDD and the typical one is 5 volts is for TTL, 3.3 volts for CMOS, 2.5 volts, 1.8 volts, 1.1 volts, and there's even lower and then there's what we call low voltage differential signaling, LVDS, which is the voltage actually just 100 millivolts, but you need 2 wires because they are differentially signal. So the programmable I/O is able to, just now the logic block, let's say the logic here is implemented in individual logic blocks, then they are routed out all the way to the specific I/O pin, and you can choose which I/O pin they route it out by the pin assignment. But that pin itself, you have a choice. You can choose whether it is 3.3 volts, 5 volts, 1.8 volts. So it's just choosing which driver it is, or differential I/O. Differential I/O requires the FPGA to actually use 2 pins rather than 1 pin. Okay, so that's why it's called programmable I/O, because you can actually specify, and it's the same way. It's just setting a few SRAM bits, which will actually enable some multiplexers to connect certain wires. And not just you can set the type of logic family, what is the voltage. You can also set what we call the drive strength. That is how much current can I push out of this pin, or how much current can I sink out of that pin, right? And this is also very important in circuits. Let's say you're going for high-speed circuits, low energy circuits, you might go for a weak drive strength. But if you need to drive very long wires on the PCB, the electronics board, you actually have to change your drive strength. So you can specify whether your pin is going for few tens of milliamps or 1 milliamp or few microamps kind of thing. And what it's doing is actually it's connecting in parallel one or more current sources. And you can also specify what is the delay of this output to the pin, how long it takes to delay to go out to the pin. And this is some level of control of if you want to synchronize the output pins, right? And you can also specify whether this input, is it going to be parallelized, right? Because sometimes you have serial input, like from I2C bus, from SPI bus. The FPGA pins allow you to actually directly serialize the bits. Like let's say you are receiving SPI bits, 8 bits, right? But you're receiving them in sequence with a particular clock. So to make the logic simpler, the I/O itself will be able to just say, I receive these 8 bits, I just have parallel 8 bits line. The parallel 8 bits lines are going into the routing logic. Okay. So now I've covered the third aspect, which is the programmability on I/O. So going back again, just to remind you, FPGA have 3 basic ways you can program it. You program all 3 of these, but you don't do anything. You specify the RTL file, the tool does everything. And this is what is needed to give you a flexible, programmable digital circuit. By flexible, I don't mean the circuit is changing all the time. I mean that if you want to implement a ping pong player game, you can implement a ping pong player game. You write the Verilog RTL, you click the button and you specify the placement, which pins are connected to the monitor and all that kind of stuff. And then the software tool will do the synthesis, the placement, the routing, and generate the bit, the serial bit stream, which is nothing else but the SRAM bits. You connect it to the JTAG, you program all the SRAM bits, and that program will actually configure, that is to set the lookup tables and the logic blocks, to set the routing between the logic blocks, which inputs and outputs of the logic block are connected to each other, and the routing, the connection to the I/O, and all those options of the I/O, whether you're going for one particular logic family at a voltage, or you're going for a particular current drive strength, or you want some kind of delay, or you want some kind of serial to parallel converter. So that is your basic FPGA. So far, any questions at this point before I jump into the next part?
No, understand.
Okay. Gentlemen?
No, sir.
Okay, if you understand, good. Now, that's the FPGAs in the middle of their development. Like I would say roughly 10 years ago, FPGAs were like that. Nowadays, because I told you that FPGAs can now totally replace ASICs, especially ASICs that are small to medium size, that are like between a few 100,000 logic gates to a few million logic gates. It can totally replace the ASIC. So people start to realize they can put this FPGA, they can just build entire chips off on them, like custom logic, they can put it entirely on them. And then the FPGA companies start to wonder that, if I want to build a custom chip and all that, what will actually speed up the development time? And they find that sometimes it's not so efficient for you to be trying to implement RAM. You need RAM, right? You always need RAM because It's just one of those things that in programmable logic or in some complex digital logic, you can use it, right? You can store data there and retrieve data and all that. And sometimes you want to implement an adder or you want to implement a multiplier. These are very high computational intensive circuits. So if you want to implement them from the basic logic lookup table elements, it's slow. And then, so because of this, the FPGA designer said, okay, now you are starting to, the market is starting to implement all these applications. And actually what they're looking for is they want some ready-made systems that can interface to memory, that can do the multiplication and addition. And then I actually have processor and all that. And I also want the lookup tables, the programmability, but I don't want to be able to implement a microprocessor using the lookup tables. I just want the microprocessor on its own because it's faster. So FPGA has evolved from just programmable logic blocks with routing and IOs, where all of this now is mixed together with dedicated circuits. What are dedicated circuits? Most likely you will see adders, multipliers, RAM, usually is static RAM, and this is not usually called block RAM. They're actually small chunks of static RAM that is distributed throughout the FPGA. And more advanced FPGAs will have dedicated processor. It's not implemented in the lookup tables. It is a dedicated processor, ARM or RISC-V, and also maybe a memory controller that can do DDR interface and all that, all inside the FPGA. And even like some of these high-speed links like PCIe controller, these are now being embedded in your FPGA alone, right? So example of dedicated circuits and routes is the arithmetic. So if you want to increment lookup tables, and if you've actually studied adders, if you want to implement, let's say, a 32-bit adder, you need a carry chain, right? Because the carry out will need to propagate to the next circuit. If you use the lookup table and the programmable routing, that's slow. So FPGAs today will have what they call dedicated wires, where this is dedicated just to implement the carry chain of adders. A second place where you can see this dedicated circuit is what they call the multiply and accumulate operation. So I think all of you are familiar with multiply and accumulate. You think back to your DSP, digital signal processing, where your filtering always you have to multiply certain values with the weights, then you add them up together, right? So it turns out this particular operation of multiplying with many different values and adding up together, this is a very, very common application in digital signal processing type application, which includes AI. Because like your neural network logic, the neurons itself is actually multiply, accumulate, and nonlinear lookup. Okay, so multipliers are actually implemented with dedicated circuit in the FPGA. So this is just actually showing you an example of, I have a one number A and another digital number B. I'm trying to multiply A and B. And the way I perform digital multiplication is I basically take all of A. If the first bit of B is 1, I set this all 1. If first bit of B is 0, all of this becomes 0, right? Then I use the second bit and then I shift it, and then I do all of this, shift. Then I'm doing addition this way, right? This is how multiplication is implemented digitally. Okay, and instead of doing this with the programmable logic and logic lookup tables, you can see the progression from 2001 FPGAs out to 2020 FPGAs. In 2001, they give you dedicated multiplier circuits, 18 by 18 bits multiplier, 2 input registers, 1 output register. Then later on, they give you an option where you have 4 18 by 18 multipliers, 8 9 by 9, and 1 36 by 36, and you can combine them in any which way. And then they also allow you to have an additional add and subtract strap here. And then as the FPGA goes on, the families evolve. You can see that they are more and more complex. So these 9 by 9, 18 by 18, these are fixed point multipliers. Then from 2013, you start seeing floating point 32-bit multipliers together with fixed point multipliers. And nowadays you see that there are actually a mixture of floating and fixed point multipliers with a whole bunch of registers and some additions here. Okay, so these are dedicated circuits that are added to your FPGA. And the reason you do that is given here. If you can say without DSPs, if you want to implement a filter, this is the amount of area in millimeters squared you would need for your FPGA. This is the amount of logic elements. And this is the frequency that you can achieve this. And with dedicated circuits like this, combining and working together with FPGAs, you basically almost can double the speed of your circuit and using roughly only 10 to 15% of the area. So dedicated circuits help you to implement more efficiently some of these kind of logic functions, multiplication, addition in particular, and it helps you to save space in the FPGA. So FPGA is no longer just about implementing any kind of combination logic, but literally now you can implement system on chip in the FPGA. And the most complicated nowadays is actually, besides adders and DSP, you have entire processor. The whole processor is also put next to the FPGA. And this is also the case for the FPGA they're using with Intel. It's called the DE1 SoC. And if you check out the data sheet online, you see that it's an FPGA connected together with an ARM processor, right? So the ARM processor is the most is the like kind of the extreme end of dedicated circuits together with FPGA. So you get the best of both worlds. You can actually use the programmability. You can write assembly code and implement it in the ARM. And then if you need to kind of have certain instructions that have to be run faster than on processor, you can actually implement them in FPGA. Okay, so this is where FPGAs is going. So besides the dedicated circuits, there's also dedicated random access memory in the FPGA. And this is why I told you that, again, nobody implements the ROM and RAM the way you write it, because in FPGA, there are already static RAM cells with the decoders. We talked about decoders, the read-write circuitry, the sense amplifier, and the output crossbar. And all you specify is you start specifying things like the connectivity, which values, which bits are actually sent to the output crossbars, which bits are actually sent to the input. So all these are already in your circuit. And what's actually in your FPGA? And what's actually interesting is if you look at the trend of memory versus lookup tables, there is a greater and greater, increasingly larger number of area is dedicated to memory compared to lookup table as the FPGA becomes bigger. So like 1 million lookup tables type of space, there are roughly about 120 bits of block RAM associated with each logic element. And again, here is again showing you again the kind of comparison. Now, if you were to just use the flip-flops to implement 2048 times 72-bit RAM. If you just use flip-flops, you use this many, and you take out area of 68 millimeters squared with only 129 megahertz of frequency. But if you use dedicated block RAMs, large ones, you can squeeze your implementation area to 0.22, less than 1 millimeter squared. This is almost 300 times smaller than if you just use registers alone, and you free up all these programmable resources to do more complicated logic, and you can actually run this almost 3 times as fast. Okay, so that's why designers, the FPGA is actually giving you more and more block RAM next to your logic. So you would actually kind of not just specify your logic, but you can actually enable block RAM. You can actually specify this part here, I want to call a block RAM. And the way you call a block RAM is basically, you know the Verilog, you have an instantiation of the block, right? You call the block name and then you put the pins to that, right? So for FPGA, there is a special instance name for block RAM, and you can also initialize the block RAM. And just to let you know, there are a few different kinds of block RAM. The simplest, of course, is what they call the single port RAM or ROM. ROM is you can only, the value is reset, you cannot write. RAM is you can read. Single port means you put one address, you get one data. What I want to contrast this is you have something called dual port RAM, which means that you can read 2 addresses at the same time from this RAM. So this is a bit of a special RAM. To dual port RAM means you can read 2 addresses from the same RAM at the same time. So you can actually read 2 of them at the same time, or you can read 1 and write 1. The only thing is they cannot be the same address. Either you will have a problem. Okay, so the RAM also you have a choice. It's not just one address, one data. You have the dual port RAM that you can read 2 locations at the same time. You can operate 2 locations at the same time. And quad port is you can do 2 reads and 2 writes at the same time. Okay, so a dual port RAM, a simple dual port RAM, you can do 1 read and 1 write at the same time. through dual port RAM is you can do either 2 reads or 2 writes or 1 read and 1 write. Okay, so you have a lot of flexibility and choice nowadays with FPGAs. And here we're talking about the evolution of FPGA today. It's not just programmable logic. It comes with dedicated circuits. Okay, and you can always connect any kind of combinational logic or any kind of state machine to these dedicated circuits. They are the adders, the multiply and accumulate. This sometimes is called DSP and processor core. Okay, I'm actually done with my presentation and sharing on FPGAs already. Are there any questions at this point? Do you all sort of get it? Is that helpful? Do you think you can understand what FPGAs are today? Do they seem very scary to you now?
For me, I understand, but I will need to go through the recording later.
Okay, sure,
If I have
sure.
any question, I will just.
Okay.
But Doctor, can, because we did discuss about the project, but we're not sure if we are on the right position. So can we share the screen that the resource that we found?
Yes, sure. Please go ahead and share and you know we can check and we can discuss that now because I'm done with the lecture, so we can talk about your project and what you've done so far. Yeah.
Actually, we didn't done much also, but this is the state. It's my screen sharing.
It's okay. It's okay. I check your understanding. That's also fine because we still have a bit of time. You can go ahead and share your screen. Huh?
Yeah. Just let me know if it's there.
I don't see it yet.
Let me change.
Okay, I see it already. All
So
right.
this is the one that we refer for the state transition diagram.
Okay, where did you get this from?
Just random website that I found.
Okay, this can help in some understanding, but still you would need to go in and pull out the data sheet from the Intel. You can't access, right? I've written to Yanming already, but he hasn't responded yet.
Oh, okay.
Okay, all right.
So anything we just need to edit from this state transition diagram according to the data sheet, if we can achieve, right? If you can retrieve from the website.
Right. This is actually the full state transition diagram for read cycles. So I hope you understand that read cycle, write cycle is actually a set of commands. Okay. So the transition to each of these state is not initiated by one command, but a set of commands, a sequence of commands.
Okay, understand.
Okay, and then the next thing is this is a little bit much more complicated than what I want you to do lah. Because as you can see, right, if the bank is already active means already pre-charged lah, the row pre-charge. Yihong, please
The
don't,
pre-charge is here.
okay, Yihong, can you just scroll down and just stay there, and then I can explain to you. If you keep moving up and down, a bit difficult lah. Okay, scroll down to the star there lah. Okay, right.
Okay.
Now you see there are different set of writes. There is just write with auto pre-charge, writing.
Okay.
After writing, you go for reading auto pre-charge. So there are kind of different sequences, you know, where you can actually write, then you follow by read, then you can write, then you write again, then you write single, write all that. So this is complete lah. If you can do this, of course, it's great lah. But I'm not requiring you to do this full state transition diagram. I'm only requiring you to do write followed by pre-charge and read followed by pre-charge, and specifically burst write and burst read.
Oh, burst write and burst read. Okay.
Yeah, you don't need to implement single read. You don't need to implement single read followed by write or read followed by read. I mean, just do burst read followed by pre-charge, burst write followed by pre-charge. You just pick one burst number. Don't need to do for all the other burst numbers, right? Because there's specific reasons like why I just want you to do burst. Because burst, you get this idea that you have to actually handle multiple data coming out, or you have to send multiple data in over a clock. So it's a bit complicated, but I want you to do a pre-charge after that and simplify it. Like, because the rest, if you know how to do these two, you will be able to design the state transition, the circuit to do the rest of the transition. It's somewhat similar, just have to pay attention to the logic. I don't require you to do all that, but if you want to do all that, great. If you do more than that and it's all correct and you can simulate, I got very good excuse to give you all A lah, right? Because it's great, right? Or if you think that maybe you all just want to get practice, maybe one person will do burst write followed by precharge, another will do burst write followed by read. You know, that's also ways to do it, that you all can share the basic and then your implement slightly different. It's up to you all, but my minimum requirement is all of you can just submit one together, and that is just burst read followed by precharge, burst write followed by precharge. I leave it up to you whether you want to do auto precharge or manual. Okay.
Okay, understand. We
Okay,
will
so
go through
so
again and
so doctor, basically for each operation, whether it's write or read, things that we need to consider is the commands itself, right? Where the
Correct. There's usually a three steps command lah. You actually, if you're doing a read, you need to do a row access stroke, a column access stroke, and then you have to clock out all the values in sequence, and then you have to do a precharge. If you're doing a write, is directly the column access stroke. You send in all the values, and then you do a precharge. So you have to study and you have to obey the timing because you are doing this on a real chip, so you have to obey timing.
okay.
There's certain timing requirements, and that's what makes this hard because it's no longer like your digital electronics where everything is just a clock cycle, right? It's not like
Yeah,
that.
true.
So you have to choose your clock. If you need, you have to actually break it down, like bring down the clock. Maybe you have to generate multiple clocks. So it's up to you, right? That's why I'm just giving you something straightforward like this because there's a lot of underlying things that you have to worry about. And the issue is just that after the first command, it's either it's 2 commands in sequence or 3 commands sequence. But again, the timing between commands is not fixed, it's not the same. You have to observe the timing. So how you implement that? Yeah.
Oh.
Right.
So do they have the informations for the timing for every command inside
Okay.
the data sheet?
Okay, it's in the data sheet. It's in the data sheet. So my recommendation to you is you have to work with one data sheet lah. So until we hear from India and Yanming, until we can get the data sheet from there, you just pick one data sheet and you work from there lah. Later on, if we are able to get access, you can just change the timing values lah. It will maybe be changing the clock a little bit, changing the voltage divider, the clock multiplier or the clock divider itself, but it's not going to be so much of a big change lah. Okay, so you can just pick a data sheet lah, because in the worst case, if no FPGA, you still need to do this design lah. Just pick a data sheet. I recommend you can go for a Micron. Just go for a Micron SDRAM. It's okay already. All right.
Okay, doctor.
Right, so my recommendation, the first step is you draw out the timing diagram for read and write, and you put down all the properly the actual timing values that you need to obey, when you need to sample, what is the clock period and all that. You put it down all nicely, you prepare the timing diagrams. Make sure you understand the timing diagrams and you draw them out yourselves, and then you put that in together in your report. Because yeah, the deliverables is not just the Verilog code, test bench simulation of these, plus you should prepare a brief report lah on the key parts of your design lah. So you should first step is to make sure you understand all these. You prepare the timing diagram. You have to obey that timing diagram lah. And that timing diagram will contain all the necessary bits that you have to set and change. Does that help?
Yes, doctor.
Okay. Next week or so, I will share with you all my grading rubric. And this grading rubric will be how I will grade this assignment and how I will grade the extended assignment. It's going to be similar, right? So you can see all the factors I look for and the descriptor for that. So you can add the information as needed. And if you don't understand any part of the rubric or how to do it, you can talk to me, and then just we can have a quick class and all that. Okay.
So I have another question.
Sure,
So
go ahead. Just
I
keep asking. Yeah.
no, it's unrelated to project, but regarding for our test two, will you be collaborating with Dr. Faunizu as well?
No,
Or
no.
how?
The contribution from this master's part is strictly your FPGA assignment. It's only one. It should be worth 30% of your coursework. Should be lah. I don't know, maybe Dr. Pangnizo might change it a little bit, but it's not going to run. And one question in EA. So from me, you only will expect two questions. One, which is this FPGA assignment. Second one, which is EA. Strictly. Okay.
Okay,
And
understand.
mine will be kind of the same style lah. I will get you to design. It will be something related to SDRAM. I may ask you some FPGA stuff lah, like show me how you implement this in the lookup table or something like that lah.
Oh, okay.
Right. But I will typically will be asking you to design. So you had to, and then you have to have, it's going to be a complex timing diagram. You have to draw it out. You draw the block diagram, you draw the state transition diagram, and then you give me your Verilog, you explain briefly how your design works. You have a test bench and all that. It's going to be unpackaged like that lah. But maybe for the exam, the design is going to be a bit simpler because you only have, I mean, you have one day for the whole exam lah, but Dr. Faumizo will be giving you two questions. So mine roughly should take about 3 to 4 hours lah, at most lah. So most likely it will be something that you can reuse your assignment lah, but you have to edit it a little bit lah. That's why I said focus on your assignment and understand and be able to explain all of it, and with good documentation on the timing, on the test bench and all that, and you should be fine for the final exam for my part. So I'm not involved in test two.
Oh, okay, understand. Yeah. Thank you, doctor.
All right. More questions at this point? Okay, if there are none, maybe we can end a little bit early today. I will share this video on Ulen X. The slides are already there. You can go ahead and check it out. Please feel free to WhatsApp me. Keep me updated lah in your progress. Again, if you just want to have even a 15-minute session just to check your understanding like today, it's no problem. Just let me know and then we try to agree on the time. Okay?
All right, no problem, doctor.
All right.
Okay, doctor.
Gentlemen, any other questions from you? I know Yi Hong's been asking, Human asking a bit. The Iqbal and Zulfikri, you're okay?
Okay, doctor.
Yes, okay, doctor.
Okay, great. So, okay, take care, and I hope you have some fun and you learn something with this. Okay.
Thank you, doctor.
Thank you, doctor.
Take care. Bye.
Okay, you too, doctor.
Thank you, doctor.